Welcome Math 107 students to the class activity for lesson number 8. We begin our class activity with some information for you that you could put into your notebook, and it's information about complex numbers. A complex number is a number of the form a plus bi, where a and b are real numbers. And below this you see 4 examples of complex numbers. The first example, 2 plus 5i, is a complex number. We call 2 the real part of the complex number and 5 the imaginary part, because notice after 5 we're multiplying 5 by I, the imaginary unit. 3 minus 4i is another example of a complex number. And then we see the situation where b is equal to 0. And when b is equal to 0, this simplifies to 5, a real number. When a is 0, this simplifies to minus 7i, an imaginary number in the complex number system. So, what's the story here? The story is that all real numbers are complex numbers. Before we knew about the complex number system, we just called real numbers real numbers. However, if we take any real number, for example, 13, we could see that we could also write 13 as 13 plus 0i. So real numbers is a subset of the complex numbers, and imaginary numbers are numbers where b doesn't equal 0. So the complex numbers is now an expansion of the number system most of you have been working with up to this point. So let's take a look at some arithmetic with complex numbers. We can add, subtract, multiply complex numbers in very much the same way we do with any algebraic expression. It's possible to divide complex numbers as well, but we're not going to do that in Math 107. So remember, one of the most important definitions that we worked with so far is that I square is equal to -1. This will be used quite a bit throughout today's lesson, class activity. So the first thing we see here in 2a is an addition problem. So we can drop the parentheses here and we get an addition problem. And what we notice about addition has not changed, that we can only add the like parts of our addition problem. So 2 plus 1 are constants, and we can add those and we get the number 3. And then 3i and 5i are like, and that gives us 8i. So we add like things as we always have in mathematics. In this case, to be a little more formal, we're adding like terms, the constant terms, and then the terms 3i and 5i. Subtraction is similar, but in this case, when we drop the first parentheses, we get 2 plus 3i, but now we have to remember to distribute that negative sign through the subtraction sign through. So we have now 2 minus 1 will give us 1, and then 3i plus minus 5i gives us minus 2i. So those are the first 2 problems using the addition and subtraction of complex numbers. As you can see, it's not anything new except for you have these terms with an I in it. Now with C and D, which involves multiplication, we still use our distributive property twice. 2 times I is 2. 2 times 5i is 10i. And then 3i takes its turn. 3i times 1 is 3i. And then 3i times 5i is 15i squared. So now we have to simplify this. Again, we combine like terms. These are our like terms. So we get 2 plus 13i plus 15i squared. And this is where the important definition from up here, I squared equals -1, comes in, because now we replace I squared with a -1. And now this becomes 2 plus 13i minus 15, which is -13 plus 13i. So that's our answer here. Okay, the next one is another multiplication problem, but you might be surprised with the result of this multiplication problem. Notice something about each factor. This factor is 2 plus 3i, and this factor almost looks the same. It's 2 minus 3i. Let me remind you about a similar problem that doesn't involve complex numbers. Let's go back to multiplying something like this, x plus 3 times x minus 3. When we multiply these two factors with our distributive property, we get x squared plus 3x minus 3x minus 9. Notice our middle terms are opposites and they create a 0. So factors that look like this, where the only difference is one is addition and one is subtraction, gives us the difference between two perfect squares. Okay, so let's take a look at D. Maybe something similar happens in D. We'll see. So 2 times 2 gives me 4, and 2 minus 3i gives me minus 6i. So I'm done with distributing my 2. Now let's distribute the 3i. 3i times 2 is a plus 6i, and 3i minus 3i is minus 9i squared. So let's compare this to the situation to the right here in this box. Well, I did get my first term, in this case is 2. That got squared, it became 4. And notice I have my two terms here are opposites of each other, so those go to 0, just like they did over here. So now I have to figure out what does 4 plus, oops, excuse me, that's a minus. Let me just make a little, there we go. What does 4 minus 9i squared become? Well, remember, I squared is -1. I'm moving ahead of myself here. So we get 4 minus 9 times -1. And that becomes 4 take away a -9, which becomes 4 plus 9. So notice back here in my little box here, I got the difference between perfect squares. And now I have the sum of perfect squares. 4 is a perfect square and 9 is a perfect square. And I get the answer 13. So I can multiply two complex numbers, in this case 2 plus 3i times 2 minus 3i, and end up with a real number 13. So that's an interesting and maybe a surprising result for you. Let's move on to the next part of this class activity. And it continues to work with this idea we just talked about. This special thing happened in this last example when we multiplied 2 plus 3i times 2 minus 3i. We got a real number with no imaginary part. This happened because 2 plus 3i and 2 minus 3i are what we call conjugates of each other. The conjugate of a number, a plus bi, is simply a take away bi. So a minus bi and a plus bi are conjugates of each other. So for example, the conjugate of 3 plus 5i is simply 3 take away 5i. We just changed the addition to subtraction in this case. So part of seeing and working with conjugates is that at some point you might be able to look at the multiplication of two conjugates and instead of working through the entire process of the distributive property twice, you might start to believe you can do it and get the answer quickly once you notice the patterns. Okay, so let's take a look at the original problem we did, 2 plus 3i times 2 minus 3i. Look what we got in the end. We got 4 plus 9. That's what we got in the end. So 4, remember, was 2 square. And the 9 we could think about as, remember, we got the 9 from subtracting 9i squared, which became negative 9 times negative 1. So if you just look at the 3 here, the coefficient of the I, the imaginary part, if we just square the 3, we end up with our answer. So would that always work? Can we just square this first number for each conjugate, the 2, and then can we square the 3 and put a plus sign? Well, let's see if this works. It'd be really handy dandy if it does. So we're going to use our distributive property again. 3 times 3 is 9. 3 times negative 5i is negative 15i. Now let's move on to the 5i and distribute that. 5i times 3 is a plus 15i. Oh, great. Look, those become 0 because they're opposite. And then finally, we have 5i times negative 5i, which is minus 25i squared. So now when we simplify this, we get 9 plus 0, so we don't have to put that in, minus 25i squared, which is 9 minus 25 times negative 1, which is 9 plus 25, which again just gives us the real number 34 with no imaginary part. So if you try several hundred of these, maybe you'll convince yourself that when you have two complex numbers that you're multiplying, like in this situation, that are conjugates of each other, you square the 3 and you square the 5 and you add them together. So in this case, we have a shortcut for multiplying two conjugates that have this form, a plus bi times a minus bi. When we multiply these, we just get a squared plus b squared. So this may be the first time you've ever seen that if we went backwards from a squared plus b squared, in the past, if we had something like this, we were told we couldn't factor it, and that was using real numbers. But now we can factor any sum of perfect squares to look like this. So for example, if we have x squared plus 9, we can now factor that. We can go backwards to x and x plus and minus 3i and 3i. X plus 3i, x minus 3i. Okay. So now we come to the part of the lesson that we were using complex numbers for, so that there are some quadratic equations for which the solutions are not real numbers and our solutions are complex numbers. So let's take a look at A and B here. We see that A is a quadratic equation, and in order to solve it, we need to get 0 on one side of the equation. All right, so we've got to get 0 on one side. I'm going to add 6x to both sides. I get 2x squared plus 6x equals negative 7. And then I'm going to add 7 to both sides. Okay, so now I have my quadratic equation in standard form, or your book calls it general form, and now I can solve it. Someone might say, well, why didn't you just subtract 2x squared from both sides? That would have just been one step. And that's true. I could have done that, and it would not have changed the result at all. But this is just the way I did it. And again, you could have started by subtracting 2x squared from each side. All right, so I look at this quickly, and there are no factors of 2 and 7 that add to 6. So I'm left with having to use my quadratic formula for this. So x equals the opposite of b plus or minus the square root of b squared minus 4 times A times C all over 2 times A. So this equals -6 plus or minus the square root of 36 minus 56 all over 4, which equals the opposite of 6 plus or minus the square root of -20 all over 4. Now, to simplify this, you know you need to say that the square root of -20 is the square root of -1 times the square root of 20 all over 4. So this becomes -6 plus or minus the square root of -1. And now I'm going to take 20 and I'm going to divide that into two factors where one of them is a perfect square, 4. So I get -1, the square root of -1 times the square root of 4 times the square root of 5. And now I'm going to simplify everything. So -6 plus the square root of 4 is 2. The square root of -1, I'm just going to put these right above it, is I. And the square root of 5 is irrational, so it has to stay square root of 5 all over 4. So this represents the two solutions for x, and we can simplify it a little bit further because, as we see, we have a 2 as a common factor. 2 divides into 6, 2 divides into 2, and 2 divides into 4. So I often encourage students to separate out the two terms in the numerator and put it over the common denominator. 4 is the common denominator for each of the terms on top. Belongs to both of them. So separate this one fraction out into 2, and now you can reduce each fraction by dividing top and bottom by the number 2 over 2, which is 1. And now if you want, you can put them back together again. And these are your two solutions. X equals -3 plus this I times the square root of 5 over 2, and x equals -3 minus I square roots of 5 over 2. So if you were to write the solution set for this, it would be -3 minus I times the square root of 5 over 2, comma, -3 plus I square roots of 5 over 2. Okay, so it's a lot of work simplifying these, but once you do a few of them, you start to feel more confident in simplifying the radicals. Again, remembering that anytime you have a -20 here, you'll always have an I as part of your solution. All right, we have one more to look at here, and it's the equation x squared plus 10 equals 2 times the quantity 2x minus 1. So again, recognition of the type of equation you're solving is important. We know we're in the quadratic equation section right now, but when you take a quiz or a test or you're working on some kind of application problem later and you get an equation similar to this, you have to be able to say, I know that's a quadratic because the highest power I see is a 2. So let's work on the right side of this equation. Let's use a distributive property here so we can see what the expression is on the right side in terms of adding and subtracting. So again, this is a quadratic equation. You have to set it equal to 0. It doesn't matter which side you have your 0 on. Since x squared is on the left side, I'm going to subtract 4x from both sides first, and I get x squared minus 4x plus 10 equals a -2. And now I'm going to add 2 to both sides, so I get 0, in this case on the right side, and I get x squared minus 4x plus 12. Okay, so the first thing I check to see if I can do this easily is through factoring, but guess what? I know I'm in this part of the course right now that is the quadratic equations with non-real solutions. So since I don't have real numbers as solutions, I'll never be able to factor this. So again, A equals 1 in this case, B equals -4, and C equals 12. So let's use the quadratic formula. The quadratic formula solves this equation, this original equation, or an equivalent equation right underneath, or this equation right here. Either way you want to look at it. It either solves this equation or this equation, since they're equivalent. It solves an equation with another equation. So you always want to begin your quadratic formula with x equals. You are solving an equation with another equation. Once you write your x equals, then you can sort of skip the x equals part and just keep putting equals, equals, equals. But this is really important that you just don't start off with the minus b plus or minus the square root of b squared, blah, blah, blah. Okay, so x equals, what does x equal? X equals the opposite of b plus or minus the square root of b squared. Make sure you put that -4 in parentheses, because remember, -4 squared is not the same thing as -4 squared. This is 16 and this is -16. So if you just write a -4 squared here and write a 16, that's not correct. -4 times 1 times 12 all over 2 times 1. Now you can just keep going with the equal sign, as long as you've got your x equals here. So we get 4 plus or minus the square root of 16, take away 48, all over 2. 4 plus or minus the square root of -32, all over 2. So let's take a look at this now. We want to simplify this. This equals 4 plus or minus the square root of -1 times the square root of 32, all over 2. And let's keep simplifying now. We know the square root of -1 is I. So let's simplify the square root of 32. Well, the biggest factor of 32 that's a perfect square is 16. So that's the square root of 16 times the square root of 2, all over 2. Equals 4 plus or minus, now the square root of 16 becomes 4. So this is plus or minus 4i times the square root of 2 all over 2. That's what x equals. That's the exact solution. We can still reduce it a little bit further. With some reduction here, we see that we get 4 divided by 2 plus or minus 4i times the square root of 2 divided by 2. Again, the common denominator belongs to both of the terms on the top. So x equals 2 plus or minus 2i square roots of 2. So these are the two solutions for x. These are the exact solutions. And unless we tell you on a quiz or an exam to give us an estimate, you don't put this in your calculator and get some estimates for the square root of 2. You leave it just like this. Okay, so if you were writing this as a solution set, it would look like this. 2 take away 2i square roots of 2 all over 1 if you want, or you can leave the 1 out, the denominator of 1. 2 plus 2i square roots of 2. In fact, we don't really need that denominator of 1. I think I put it like that in the answer key, but let's just keep it like that for now. Okay, so those are your two quadratic equations that have non-real solutions. And you can see it does take a little bit of work, but the more of these that you practice, the quicker you'll be. All right, now finally, we start to come back to where we started this whole lesson with trying to make the relationship between looking at the graph of a parabola and from the graph determining whether we have two solutions, to our quadratic equation once we set it equal to 0. One solution, when I say solutions, I'm meaning real solutions or no real solutions. So if we go back to the very first part of this lesson, you'll recall that if we set, here's our parabola, y equals x squared plus 3x. If we set that parabola, the y value equal to 0, we see that this parabola crosses y equals 0, which is the x-axis, right? Y equals 0 is the x-axis at -3 and 0. So in this situation, we have two friendly solutions. Friendly being they're rational numbers. They're integers, -3 and 0. Even fractions at this point are friendly to us, right, after seeing all these i's. We also had the situation where if we graphed y equals 4x squared plus 12x plus 9, we saw that we only touched the x-axis at one spot, and that was -1.5. So this is a situation where we see that we could have two real number solutions or one, and then we looked at the graph y equals x squared plus 1, and we noticed it didn't cross the x-axis at all. So therefore, this equation right here, if you were to solve this equation, x squared plus 1 equals 0, you would have solutions that look like this, x plus or minus I. Okay, I just saved you all the work and did that for you. Now actually, if you're making the connections between all the pieces of this lesson so far, you could see that you could factor this expression x squared plus 1 because x squared is a perfect square and 1 is a perfect square. And you could do it by factoring it into the two conjugates. And then you set each conjugate equal to 0, and you get x equals I, and x equals the opposite of I. So the solution set here is minus I and I. So that's why you don't see this crossing the x-axis at all. Again, this type of expression, x squared plus 1, you now can easily factor using these conjugate type of factors. Okay, so let's go back to the class activity. So note, there are a few different types of answers we might get when we're solving a quadratic equation. Read the following, ignoring the blank lines for a moment. So as we've seen with that first graph in the preview exercises, we could have a graph that crosses the x-axis twice, and we get nice friendly numbers for our solutions. We could also have one rational number for our solution when we had an example of a parabola in exercise 1b of our preview exercises. Sometimes we get our parabola crossing the x-axis, but it's not at an integer or a number we can easily determine, and that would be when it's irrational numbers. And then finally, we can have an example like number 2 in the preview exercises where our graph doesn't cross the x-axis at all, and that's when we have non-real solutions. So the types of answers you get from a quadratic depend only on what happens under the square root, under your radical. In fact, if you look at this expression, b squared minus 4ac, if you look at the value for that, then you'll know whether you're going to have non-real solutions or real solutions. We call this expression b squared minus 4ac the discriminant because it discriminates, it differentiates, it determines what type of solution you're going to have, real or non-real, two solutions or one solution. So let's go back to these blanks and then determine which of these following inequalities work for the situation presented up above. So in other words, if we have let's start with this last one. If we have two non-real number solutions, what must be true about the discriminant? the expression that's under the radical sign? Well, we know that the expression under the radical sign would need to be a negative number. So that means b squared minus 4ac will be less than 0. It will be a negative number. That's the only time in each of these 4 bullets here that b squared minus 4ac is less than 0 when we have 2 non-real numbers. Okay, so we can check that one off. Okay, what about the situation where we have 2 rational numbers that are nice and friendly? Well, that's when we get a square root of a positive number, but the positive number, to make this nice and friendly, happens to be a perfect square. So in other words, square root of 9, for example, will be 3. Square root of 9/4 would be, of course, we know this is plus or minus in all these situations. That would be 3/2. Again, rational numbers. So this is a situation where b squared minus 4ac is greater than 0. And you can even go a little bit further and say b squared minus 4ac is a perfect square, a number that's a perfect square. So 2 irrational numbers is again a situation where you have plus or minus a positive number. That's not a perfect square. So in other words, you'd have something like plus or minus the square root of 5. That's not going to be a nice friendly number. But again, the discriminant here is still positive, just like it was in the first bullet. And finally, when do you get one X-intercept of one solution? That's when the discriminant is equal to 0. So when you're adding and subtracting the square root of 0, you only get one result. You get plus or minus 0. So this is a situation when the discriminant is equal to 0, you have one rational number. So let's go back here to these examples, and particularly B here. I want you to see the discriminant so that you can see an example, because you could write 4x squared plus 12x plus 9 as 2x plus 3 quantity square. So this is a situation where, since this factor 2x plus 3 is identical, 2x plus 3 times 2x plus 3, when you set that equal to 0, you're only going to get one solution. But this is where your discriminant is equal to 0. So let's take a look at this. B is 12, 12 squared minus 4 times A times C. So we get 144 minus 16 times 9 is 144 minus 144 equals 0. Okay? So whenever your discriminant is 0, you only have one X-intercept, and therefore you have one solution. And finally, in the class activity for lesson 8, we're tying this all together with the graphing connection that X-intercepts of the graph y equals ax squared plus bx plus c, so this would be a parabola that you'd be graphing. The X-intercepts can be found by finding the solutions to the equation ax squared plus bx plus c equals 0. In other words, you make y equals 0. That's how we solve our quadratic equations. The connection to y equals 0 in terms of our graph of the parabola is the X-intercept, because all X-intercepts have y equal to 0. So do you remember how to find X-intercepts on either your TI graphing calculator and/or in GeoGebra? If not, check out lesson 3 and you'll have a reminder. So let's take a look here. In the left-hand column of the table below, describe what must be true about the discriminant in order to obtain the solutions in the middle column in the graph in the right column. Okay, so I'm going to give you a few minutes to fill this in, and then I will turn the video back on with the left-hand column filled in. Okay, so hopefully you have the left-hand column filled in with these values for the discriminant: greater than 0, equal to 0, and less than 0. That completes the class activities for Lesson 8. Let me know if you have any questions.